cool. So I'm Dave. This is a cozy environment, so feel free to ask questions, interrupt me at all times. There's tons of, this isn't very serious talks. There's tons of cat gifs and things like that. So to entertain and to inform all at the same time. So the title is Reactive Layout for User Interfaces. I kind of changed the title in the last hour, but it's all about animation and layout on the web and doing it at 60 frames per second, especially when the app experiences that you're trying to make have a lot of gestures involved, a lot of animations that are happening at the same time in a coordinated kind of way and doing that performantly on the web. So avoiding reflow and things like that that make the web janky. Denied. Okay, so the title was Reactive Layout for the web, and I want to, I don't know what that beat was. Yeah. The title is Reactive Layout for the web, and I don't know, how many of you guys have heard of something called reactive programming or functional reactive programming or something like that? Cool, a few of you, and it doesn't really matter if you haven't. I'm not going to be, this isn't a talk that has a lot of complicated words that are of a particular technical aspect or something. But I will just give a brief overview of what that kind of means and why it's useful for layout. So the way Wikipedia defines it is a programming paradigm oriented around data flow and the propagation of change. Okay? So visually what that means is that your app looks something like this. One giant pipeline, not really though, right? One giant pipeline and things are just kind of flowing through the app. So I won't insult your intelligence or anything, but over here you can obviously tell that's your isomorphic JavaScript, like later in React. And in the top left, that's your backend REST API, right, obviously. And who can tell me what this is? That part? You don't see that? Testing framework, obviously. Okay, great. But we really want to know what this means when words hit the page. Okay, what does it mean to code in a reactive way versus a non-reactive kind of way? So the opposite of maybe this reactive programming thing is an object-oriented programming. So let's do something really simple. We'll have a tree, okay, and we can make it fall. It'll have some state. It'll say whether it fell or didn't fall. So this is ES6, but it's kind of a pseudocode. It has some getters and setters, and you just set the fall and state to true, and your tree is now in a state in which it had fallen, okay? Let's contrast that, though, with a reactive way. And what I'm not trying to show here is just less lines of code. It's just a different kind of way of thinking. This tree will extend this thing that emits events, okay, and the way that the rest of the world knows what's happening with the tree is the tree just emits these events. So it emits that it has fallen, okay. This doesn't by itself do anything because nothing is listening to the tree at all. So maybe there's the ground, and the ground listens to the tree, and when the tree falls, then the ground does something else. So we're starting to build a pipeline, beginning with the tree, and then there's ground, and there's blah, blah, blah. So if I ask you guys a really philosophical question, okay, something I thought about for a while, if a tree falls in the forest and no one is there to hear it, doesn't make a sound, who says yes? Yes. There's no right or wrong answer. That's exactly right. So, well, who would say no? Awesome. All right. So it seems split in the tree case. In a universe far, far away, some tree falls, no one is there around to hear it. Does it actually make a sound, or has it even fallen? You can ask. Anyway.
Philosophy major want to take.
So, but this is the codification of those two philosophies in a nutshell. Okay. Usually, when no one's there to hear the tree fall, a person will say that the tree fell because they can just go to the forest eventually and be like, "Look, there's the tree. It fell. I know that it fell." That's proof that it was the fall, even if I wasn't there to observe it. And that's what happens on the left-hand side. You can always ask, what is tree.fallen, and it will return true or false, depending on whether it fallen or not. But if you're not there to hear that event on the right-hand side, then you have no idea whether the tree fell or not. So the crux of this all is about state. In the object-oriented way, state is owned by these objects. And in the reactive way, state isn't owned by any of the objects. There's no this dot has fallen. State flows through the application, okay? And it's the things that need to listen to it, subscribe to it, but they never retain any of that information. And both of these two philosophies have their program equivalents. So there's the model view controller system in the object-oriented world where you have all these different objects and they have these different responsibilities. of what they're supposed to do. And then there's the functional reactive programming approach where you build up these pipelines, okay? And this is a picture of somebody who's trying to eat some soup, and as he's eating, his napkin is brushing off the soup that's going on his face through this sophisticated pipeline. But like everything's all about, this isn't supposed to be funny, but everything's about like inputs and outputs. There is no, the parrot over there gets the bread hit on him, and then he does something that then passes it off to something else, passes it off to something else, and eventually the napkin does something, which is wipes the schmutz off of his face. So the patterns here are in the MVC world, everything's about objects, getters, and setters, and state. And in the functional reactive programming world, things are about functions that are processing in this pipeline. And what's moving through the pipeline are events. All right, so that's kind of the really low-level philosophy of the differences between the two things. But let's talk about what this actually has to do with making user interfaces, and particularly ones that change at 60 frames per second, change continuously in some way. So like this Bruce Lee of UI design, we can think of UI as a pipeline. Okay, it starts with the user touching something on the screen. We do some question marks of Kung Fu, and then something changes on the display. That's true for user interface all the time. Like that's just what an interface is. But something happens when we think about this in a continuous kind of framework. When the way that people touch the screen is like they might scroll something or drag or they'll do a gesture. There's continuous input happening. It's not necessarily that they're just clicking on a button and that's like one thing happening at one point in time. Scrolling is continuous. A lot of these gestures are continuous. And what I want to do is make animation on the web track the user in a continuous kind of way. And the functional reactive stuff is much more built for that because it's all about continuously changing data that flows through an application. So when you think about the visuals of your app, each little part that might be animated and moving around the screen, it's like the X and Y positions of it are changing as it's animating. And so the X and Y positions don't belong to that little thing that's animating. That's belonging to the kind of display that's putting things on the screen. And those bits of information are just kind of flowing through the app as animation is happening. So the first part was about getting user input. And the DOM starts us off here. The DOM gives us what are asynchronous streams. Like Node popularized the idea of async streams, but every time you add an event listener and listen to mouse move, that's exactly, you just get this stream of data as the user is moving the mouse. And the same is true for touch, move, scroll, resize. All of these things are just streams that the interface is providing you to begin with. Yeah, so there were streams all along, but there's a problem. What's useful about streams or thinking about these pipelines is that you can transform one pipeline into another, one stream into another. You can branch them, you can merge them back together. But in the DOM, the only way to add extra logic into that stream is to literally write that in that callback function we saw in the last slide. So it would be a lot cooler if we could think of subscribing to the mouse position or subscribing to touch or whatever it is. So you can have little pieces of your layout that listen to the mouse, or maybe you build higher level streams on top of these lower level streams. You can have something that tracks a user's touch as they cross the screen, and it'll be a swipe left gesture that it recognizes, or maybe a circle or something like that. Or you can take some motion and map that to a velocity. How fast is the user moving? Because maybe I want to have some bounce effect when they let go of the page. Or maybe you want to do a pinch to zoom. So you're tracking two fingers and you want to say, like, well, what does that mean if I'm trying to, how much is the user pinching? Or doing something like that. So this is the kind of API that I'd really like to see for doing more interesting things for layout on the web. So I have this little demo. So here, as I'm dragging this bar, a lot of different animations are kind of happening. This little side menu is being revealed, but also the opacity of the nav bar is changing, and a bunch of things are kind of translating right and left. And everything that's happening as I do this, and I can let go. well, that's interesting. But I can always just go to the one that I know that works. Okay. So everything is moving coordinated and in sync. Okay, and this is like the interface that you see in your native apps when you press the back button in the settings panel, like things opacitate out and one screen translates in while the other one moves out, and it's all happening continuously and fluidly. And scrolling is a natural behavior, but we're seeing that in all sorts of gestures that come up inside of our interfaces. And the way that this works is like first the mouse is this blue thing is listening to the mouse, and then it's clamping the mouse position at some point, because I can't scroll too far. And that blue guy is emitting a bunch of numbers between 0 and 1. Okay, and eventually it clamps and it's just emitting 1s. And then the side menu is listening to those numbers and it's translating itself. And then the nav bar is listening to those numbers and it's opacitating or it's also translating. So it streams all the way down from the mouse to each layout thing. They're all listening to the same number, 0 to 1, that's changing and then updating themselves. And that's how you can do a lot of coordination when it comes to your animations. Right now, the only thing that you can kind of do in animations is you like toggle a CSS class on or off, and maybe something will animate. But you can't have some other part of your screen listen to the progress of that animation and respond accordingly. So it's kind of like you can change one thing at a time, but you can't unify all of them inside the application. All right, so I'm trying to, I want to make this talk like useful for everyone, whether you use my library or not. I don't really care, but I am building this JavaScript library that tries to do it. And I know that maybe like the common reaction is like this, right? But you know, and I have that reaction too. I completely sympathize, except it's my library this time, and so I don't have that reaction. So the library is called Samsara. It's on GitHub. I recently released it a week and a half ago or something. That's what, as John said, MIT license, totally free, and try it out. But if you feel like this little cat here with like fatigue of the JavaScript fatigue, then you know, like I said, I totally sympathize. But for the rest of this talk, you're going to be pretty bored and feel like you're just being dragged across the ground like this. So let me tell you a little bit about the principles of a library and like how it kind of works. And the first one is that layout is done in JavaScript. Usually we think of layout as being part of CSS and HTML, but well, I should clarify, layout that animates is part of JavaScript. You can still do all the CSS, HTML things that you want, but when things start moving at 60 frames per second, it's the preference of the library that it gets control over how these things move and how to coordinate them together. So in order to take this away from the DOM, to get away from reflow and repaints and stuff like that that ruin 60 frames per second and performance on the web, we absolutely position everything in CSS, and we manually position it in JavaScript. And we do it in an accelerated kind of way. So we create this thing called the render tree. All layout is a tree because things are always laid out relative to other things. You want something to be beneath something else or to the right of something else, so you have this parent-child relationship. So we build this tree inside of JavaScript. Kind of like the virtual DOM, it's just like a low memory footprint of what the app looks like, but just presentational. So we build up this tree, and at the bottom of this tree, I'll go into this in a little bit more detail, is the DOM. It's like, all this tree does is it exports three things: a CSS3 transform, an opacity, both of those are hardware accelerated, and a size, which is not hardware accelerated, but you can't really do layout without having widths and heights of things. So that's all it does. And it inserts these things into the DOM at the end of the day. And all of the animation and stuff is batched behind a request animation framework. So this makes sure that you can get that 60 frames per second and your app is being recycled with the actual refresh rate of the monitor. So that's the layout done in JavaScript part. Then this is not necessary for the framework, but this is like why I'm excited about making it, is that the entire thing is one big stream. So from the moment that the user touches the device to how that information cascades through the render tree, creating all this layout stuff, and then how it's eventually outputted into the DOM in terms of those CSS styles, that's all one big stream. So the second the user isn't touching it, nothing is happening. The second that the user is doing some gesture, everything is moving consistently coordinated. And the last thing is it has nothing to do with content. So you can use React or whatever library you want, a handlebar template, to actually talk about the content of your application. The only thing that I care about are rectangles moving on the screen, like X and Y positions, heights and widths. I don't care at all about what's actually inside of these boxes, just how these boxes move. So this is how the render tree is just a bunch of nodes, the leaves of which are DOM nodes that you attach. So you have some DOM nodes on your website, and this tree is going to inject a bunch of styles into those nodes. And the way it does it is you give some kind of layout information into these nodes, translate properties, scales, skews, opacities, whatever. And at the end of the day, these things will be flattened and put into the DOM. So that div on the left will have some final translate of 150 by 200 because it just combines the translates of the ones above it. But we can make up our own primitives here. It doesn't have to be translate. We can talk about things like size and alignment and things that you normally want to do with layout. You want to center things or float things right and left. So here, a line is relative to some parental size, and all it means is like distribute this thing into the center of that size. So if you were to combine those things down, you'd have a translate of 25 by 25 coupled with the very top node, a translate of 100 by 200, and when we flatten that all down, you get 125 by 225. So you build up this tree, you can individually change nodes. So if I individually change that top node, both those divs on the bottom will move. But if I change one branch or another, then it'll only affect that node on top. So let me give you a demo of kind of how this works. So I'm talking about this render tree. Why don't we just build an actual tree just to show you how it works? So if this is some big fractal tree of 256 DOM nodes, if we look over here, if we expand down, we'll see the DOM is totally flat. I'll make this a little bigger. All these things are on the exact same level as I cycle through. So if you were to build this yourself, you might have 8 layers deep of DOM nesting because everything is relative to the thing above it. And you can build some fractal thing. It'd still be hard. So everything is flat. All the layout is done inside of this render tree. So the JavaScript part is nested, but the output is flat. So that's really useful for performance because the DOM takes a long time to figure out how to move something if it's dependent on all of the things that are above it, all of its parents, because they also have to, one parent moves and all the children have to be recalculated. So if you keep things flat, that's useful for performance. That's how native apps are built. Inside all of these is content. Like this is actually rendered from a handlebars template just for fun. I put little smiley faces inside of some span tags. What's important is not, like, since the smiley face isn't animating, I don't care about it. That can be in a very nested structure inside of something that is animated with Samsara. And this is useful for even your own apps, whether you use Samsara or not. The more nesting you have in your DOM, that's a boon to performance because it puts more effort that the browser has to do in order to relay everything out when things move. So I'll close this guy for a second. But the cool part is that we can make this thing animate also. So in everything that I've shown before, all those styles were static, but this is JavaScript. You just make those numbers change, and everything is going to cascade down below them. So when one branch moves, it moves all the branches on top of it because in JavaScript it's nested. So when one number changes, then it will affect all of its children. And you don't have any of those reflow and recalc kind of properties. Okay. And that's 256 DOM nodes that were all animating at 60 frames per second. Right there. So this is how animation kind of works. You have this tree, is what I was briefly describing before. In Samsara, you call it a transition. Well, it's just some number that changes from A to B. usually with some easing curve. So we can map that number into a different translate, or map that number into a size. And as that number is changing, those layout primitives that are inside of these nodes will just change, and the whole thing will animate. That's how the previous example kind of worked. Any questions?
What about interacting with the elements and clicking something?
Yeah. So do I have any? I don't think I have any demos of that. I have plenty in my CodePen and stuff. But yeah, so any element can listen to any sort of event, and then those are themselves streams. So as you're dragging something, there are primitives in the language here that'll tell you how far you dragged, what are the current X and Y positions, and all of those are streams. You can map that to a layout. So if you wanted a div to just track your finger, you'd be listening to that mouse move event or touch move event, whatever it may be, mapping that into a layout, which means just translate it by how much I've moved, the finger has moved, and then it will follow your finger. That's kind of how that works.
My question is more about calculating the depth when you have things laying on top of each other. What are you touching that's covering the element?
Yeah, so it's totally fine. Like if your node is on top and it has all those things underneath, and you move that one, then they'll all move. Like everything's done in JavaScript. All the hard stuff is done in JavaScript instead of the DOM, so it'll handle the performance for you because it's just numbers. It's not doing reflow and recalc and updating the DOM. It's just all in memory. So there's also physics into the library too, so you can translate something with an easing curve and ease in. Oh, I didn't update the slide. Sorry, there's a primitive. You can make the curve say spring and give it like a period and a damping, and it'll do like a springy animation or something like that. There's plenty more. So you can think of the render node as being this top-down thing, but it's actually better to think of it as left to right. You start with some stream, either that transitionable thing before or user input, like you were mentioning. It goes through these nodes, and each step of the way, those nodes are just one stream transform into another. So if one node has a transform and the other one has a transform, then the way that it trickles through the system is it'll compose at each step. So those transforms will multiply because they're CSS3 matrices. Opacities will just scalar multiply, or size and align will combine in ways that, like they're percentage based. One will multiply by first align value will multiply by the height, and the second align value will multiply by a width, and it'll end with some translate. But the whole thing, you can think of it as from user interface through this render tree, and then eventually into the DOM. Just one big stream. Functions are just composing it the entire way down until the very end. You get transform, opacity, and size. And this opens up to the idea of coordinated animation. So, like I was mentioning to your question, like if you have these two CSS classes that are both animating, how do you sync them together? Or how do you make one depend on one another? Like how do you do the cause and effect relationship? But with streams, it's super easy. You just pipe it to two different places. Or maybe you, in the process of piping it here, you transform it, you like offset it by 50 pixels, like that's fine. You can do you can filter it, you can do all these stream-like things, and it's really easy to coordinate animations together. There are many like JavaScript libraries where you take one element and it allows you to animate its opacity with some easing curve. But it's really hard to do that and opacitate this thing while you're translating this guy and like feel like you're the conductor of an orchestra instead of just the player of a single instrument. So the clear app, who's ever used the clear app? Nobody? Or have seen it or something? Yeah. Like I really feel like the clear app was like way ahead of its time. It still is. As this app that has no buttons, like you don't click on anything, it's all gestures, and it's extremely intuitive. You like pinch something to have a new, it's just a to-do list item. So you pinch up to include a new one, that's that animation right there. You swipe to delete, or you swipe the other way to do something else, or you can zoom out. You can do all these things that are all, there's not a single button in the entire app. That's the whole point of it. And these are the kind of apps that I'd like to see more of. And you see a lot of people making apps like this. Like, it's React or Angular or Ember or Backbone or whatever. This is not the problem they're trying to solve. This is the problem that like animation libraries are trying to solve, or things like Framer or maybe GreenSock. But there's still like the idea of coordinating all these animations together, having a lot of things moving all at once, tying that to user input. That's the like greenfield territory that I think we should really explore. Do you have a question? Or? Oh, okay. And these are the apps that I'd love to see kind of made. People are making them in the native world, but believe it or not, we can do this kind of stuff for the web also. The one on the left even has things popping out of the phone. How do you do that? I don't know. We'll see it.
Question as well.
Yeah, Samsara can do that for you somehow. I think it'll happen right here. Yeah, out of the phone, 3D, that kind of 3D.
Just breaking the fourth wall.
That's right. Yeah. I should have even pop outside of the frame.
You, that's when it hypnotizes you, and convinces you.
Yeah, better watch out. It might come right in my face. So yeah, I have this other. So all of these are actually also on the website, and you can even do them full screen on your phone if you go to Samsara.js.org, or even through the GitHub. Just letting you know. But on iOS, if you've ever looked through the tabs, for your Safari tabs, it looks something like this. And as you scroll, like things kind of recede in 3D space. And it's all tied to like, you don't just have to scroll something up and down. Things can move in 3D, they can animate as you scroll. This has always been hard for the web, but because of the jank that was kind of always introduced with hijacking scroll. But if you think about it the right way, you can all do this in a very performant kind of way. When you click on one of these guys, it goes full screen. And the way, like I can actually still scroll here, and the way that I'm doing this is like, so the scroll view that this is all in is accommodated for the larger size of this element because now it's full screen. But I didn't actually write any code to handle that. Just by the fact that the size of this New York Times article is growing, the scroll view is listening to that because the size is listening to all the streams that are plugged into it, and size being one of them. So it's allocating the space based on all the streams that are connected into it. So as one stream enlarges, it just allocates more space. I can delete this guy, and all I do is I animate its size to 0, and the scroll view shrinks. Like there's no other logic that you have to do. You don't have to like think about how this all works together because everything's just has all these passive listeners that are already there. And you have, like on touch, it's really a pain in the ass, but you have like these bounce to refresh and the inertial drag, and these are all the physics simulations that are happening underneath. So I'd love to see web apps do more of this kind of stuff. Okay, so this is coming to the end of my talk. I don't know how long I don't know how long have I already talked. All right. So the vision, right, that I'm trying to sell here is that like we've always been thinking about interfaces in terms of point and click because we've always been using a mouse. Okay, and we've been using touch for a long time, but we still haven't thought. Like only recently are we thinking about interfaces being point and move, like that the interface evolves with the user as they're interacting with it, as they're touching it. You don't, when you want to throw a rock at your best friend, you don't click on the rock and then click on your best friend's face. Like there's thousands of muscles that are all happening continuously and like, creating this visceral emotion of you hitting your best friend with a rock. So, and it's more than that. I actually think that like if we move away from these click interfaces, we're doing ourselves a good deed, because when you click on something on a website, the website like does this. Like who knows what's going to happen next? It might be a whole new website. Maybe you're just revealing some more content. You're going to a next page. Who knows? It's like you derive it from context. But when you're scrolling a website, you do this and the website does this. Like there's a one-to-one relationship between what the user is doing and what's happening on the website. And I think that the more our interfaces use continuous gestures, the better, the more intuitive they're going to be. So lastly, this is how your users behave. Think of your users as they're moving in these awkward, continuous ways and not clicking on things. We're calculating something.
What is this mean?
This is something about
You have I don't watch. No, I.
No, this
I should. I should.
So thank you.
I don't think